Hey, what up, guys? It is Nick the Quant. Today, I have another video for today's highest mathematical edge pick. Yesterday, we had the Giants again on the money line. I mean, all my picks yesterday were very close games, all decided like right towards the tail end of each game. Giants played exactly as the math showed. My model had the Cubs as being significantly overvalued. Even showed mathematical value slightly on the Giants, which exemplified very large pricing advantage present on that Giants side. It was the second day we took them in a row. Fortunately, the Giants lost in the 10th inning, bottom of the 10th. Cubs walked it off and won, or got a hit and won, so they beat the Giants 3-2. It is what it is. The streak ended. We were going on a vicious streak of winning these highest mathematical edge picks, but I have no doubt that we're going to get right back onto that path. Yesterday, overall, I went 1-2 and lost a little over 2.4 units. That's my first losing day in over 5 days. So performance has been pretty insane, but you can't really expect that to sustain forever, especially in sports. So saying that, we can get into today's highest mathematical edge pick. So today, we got the Baltimore Orioles on the money line. And I just want to be able to give you guys the odds real quick because of my notes. Or my program, it shows the most previous game I ran, which was the Tigers game. So here we are. So yeah, we got the Baltimore Orioles on the money line. We got them at plus 118 odds. The model is giving them a probability of a 52.8%. So despite them being an underdog, a pretty solid underdog at plus 118, my model is showing mathematical favor in the Orioles, which will then just bring about how much of a financial advantage there is on the Orioles here in a second. So because they're plus 118, we got them at a 52.8% probability. The Orioles' expected value is a 15.1%. Using a fifth Kelly, we're going to be risking 2.56% or 2.56 units for a potential profit of 3.02 units. So we can jump into the math now, like I always do. Take you guys through the ensemble model. I'll take you through the 9 interior models. And then we'll go through second and third layer calibration and just kind of bring it back full circle. So again, real quick, I always like to preface this. The 9 interior models, my ensemble model, are calibrated based off of the actual historical, or should I say empirical results of the initial predictions. So I always like to use an example. So I ran the Braves game today, for example, and couldn't really find edge in it, but Model 1 initially had the Braves at a 59%. That's been hitting up to this point on the season at a 64.56%. So Model 1's probability for the Braves is a 64.56%. Now, how much that model is weighted, meaning how much it influences that initial total probability we get, is based upon how reliable that probability is right there, or how reliable the calibration is, that 64.56, which is denoted by how large of sample size that 64.56% is pertaining to. Larger the sample size, the more reliable. Less sample size, less reliable, because now there's just potentiality for a lot more variance. And then once we get the second and third layer calibration, I'll explain those. But I always like to explain that if you're a new viewer. And honestly, the term I am going to start using for the way my model works is just reliability modeling. It's something I kind of think really well defines as far as how the calibration works. All right. Fighting a yawn. Okay. So the first model has the Blue Jays at a 49.43% probability. Model 2 has the Blue Jays at a 55%. Model 3, Blue Jays 54.7. Model 4, Blue Jays 54.72. Model 5, Blue Jays 62.96. Model 6, Blue Jays 50%. Model 7, Blue Jays 46.67. Model 8, Blue Jays also 46.67. And then Model 9, Blue Jays 59.26%. So my ensemble model, using those calibrated probabilities and the reliability of each, produces an initial prediction or an initial probability for the Blue Jays of a 53.49%. So now we use second layer calibration, which takes into account how my ensemble model's probabilities have been performing. I use empirical Bayes, so what that does is it takes two things into account. The first being that ensemble model's initial probability output, and then the amount of sample size, or just the, not the sample size, sorry, the actual results. how it weighs as far as the calibration goes, as far as like, is it going to rely more on what the model's saying, or is it going to rely more on what's actually happening in the real world? Very similar. The more sample size we get, the more we want to just rely on what actually is happening in the real world. That's the ideal form of calibration. So as you know, data just continues to increase and increase and increase and increase. Empirical Bayes shifts to what is actually happening while still taking that, the what the model's saying into account, but how much weight it's giving that starts to decrease. And over here, what's actually happening starts to increase. So saying that, when my ensemble model produces 53% probabilities, they're only hitting at a 41% hit rate. So the calibration for the Blue Jays now is a 49.07%. So you can see if it was my interior models, it'd be a 41%. But because it's empirical Bayes, it's taking into account what the ensemble model initially predicted, that 53%, right? And then its win rate, 41%. And then it says, how much sample size has there been? Not a ton. This is my first season betting on MLB. So empirical Bayes pulls it down still notably to a 49.07%. Now we get into our final layer of calibration, which is taking into account the market region that the Blue Jays fall in. The market region the Blue Jays fall in today is the worst performing market region that I've been tracking. It has only a 43.68% hit rate. So it definitely has been struggling relative to the market. That's very disadvantageous, but relative to the Blue Jays pricing as a favorite, extremely disadvantageous. And the complement of that, which we can just kind of round up and say is 56%, which would be the opposite side. In this case, the opposite side of the market region being a 56% hit rate, would apply to the Orioles, who at plus 118 or whatever those odds were. 1 second. I believe plus 118. I'm trying to remember everything. Yep, plus 118. Very advantageous. Extremely advantageous, actually. So we apply that third layer and final layer of calibration to the Blue Jays, and what it does is it finalizes the Blue Jays at being, finalizes the Orioles, like I said, at a 52.8, which makes the Blue Jays a 47.2% probability. So the Blue Jays, despite being favored, are 47.2% probability, the Orioles being a 52.8. So that is explaining the math, how my model came to this conclusion. So again, we got the Blue Jays, 52.8% probability the Orioles, 52.8% probability on plus 118 odds for an expected value, strong expected value of 15.1%. We're going to be risking 2.56%, or in other words, 2.56 units for a potential profit of 3.02 units. As always, if you want access to all of my free sports betting picks, you can go to my X account at NickTheQuant44, where I post all of my picks, not just this one for my highest mathematical edge pick. And to give a little bit of insight, my highest mathematical edge pick takes two things into account: the expected value, but the amount I'm risking. Usually how I go about this is my highest edge pick is the one I'm going to have to risk the most on. So in this case, the Orioles, I'm risking the most on today at 2.56%. So if you're looking at my X account and wanting to say, okay, like, which one is the highest edge pick, and you haven't looked at my Instagram, which Nick the Quant, my Instagram, I post my highest mathematical edge picks daily, but let's say you haven't, whatever pick has the highest risk, I view as the highest mathematical edge pick. Someone could argue and say, well, no, the one with the highest expected value should be the highest mathematical edge pick. That's also valid, but the only thing with that is you could have a ton of expected value, but my model not favor the team, but it's because they're such a large underdog. Like if you have a team who's plus 170, my model's giving them a 47% probability. That's significant financial advantage and significant expected value. But if you have another one where you've got a team who's like minus 105, but my model has them at a 62% probability, there's still going to be significant financial advantage, but the expected value will not be as large because expected value, again, is pertaining to long-term, probability distribution-based decision-making. Whereas when you talk about mathematical edge, you are talking about what's the mathematical edge in this specific matchup. So that's a little bit of the difference right there that I think I have not explained yet. So I would like to kind of offer some insight into that. So other than that, cheers, and thank you for watching.